to use EFL and elementary. EFL itself looks something like this. You have a bunch of libraries, higher level sitting on top, doing everything from graphics, even audio, asynchronous I/O, dbus, graphics layout, etc., etc. A whole widget set at the very top, that's elementary. At the bottom, data structures, lists, and so on. Virtual machines, compiler, some data structure handling, and something called EO. And that is kind of what I'll be talking about. This thing there. It's nice and short. It actually stands for the EFL object model. And now that's what we're covering. So we have had an ad hoc object system put in place. EO formalizes this. It puts it in everywhere. We had kind of pseudo objects that we built as we needed, all our timers, animators, our actual graphics objects. So from Evis, which is the canvas layer, all the way up. So Edge built on top of the Evis objects. You inherit a bunch of methods, so when you move, resize, and mess with them, the Edge code can override that and implement itself. Certain other ways of doing these functions. Elementary inherits yet another level up with elementary widgets, so your buttons and so on, and etc., etc., etc. We have lots of different stuff there, but it was done relatively ad hoc. EO now puts this all together with a single object model going all the way down, all the way to timers and animators, etc. It is done in C, not in C++, so all the core toolkit is still C. But what it does do is it starts to look a little bit more like a dynamic language rather than a C++ kind of world. You have now call safety, so if you call a method on an object that doesn't inherit or handle that interface, then you basically don't have any problem. It's not going to fall over and die. It won't detect at compile time, it does detect at runtime. If you access an object that is invalid, been freed, deleted, or is an object of the wrong type, that is also handled and safety is maintained. It deals with that. Now, the cool and interesting thing is that this object model actually translates directly to C++ in most ways. So we now are actually supporting generating bindings automatically without any extra human intervention directly into C++. So you can now use C++ with the same classes, methods, the same hierarchy, and the same method names, etc., 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 the same way you do in C. We are also going to be adding Lua soon as well. So as an object model, it actually does quite a bit. It does both single and multiple inheritance. It does plain interfaces. You can do mix-ins, build things on the fly. Every object is reference counted. You've got weak and strong references. You can have cross-references between objects, so if one deletes, the other one will auto be deleted, or vice versa. It does all the event callback handling. So if an object has an event, you can trigger it and it will call everyone who's registered for that event. Also deals with adding and deleting and managing the actual event handlers themselves. It deals with the whole parent hierarchy thing. You can add arbitrary data to objects, key value pair. So you've got some arbitrary key, you want to tag the data on the object. If you do it right, it'll get auto deleted if it's another object when the object that has the data is deleted. All of this has runtime checks. So accessing an invalid object is actually safe. It's very unlikely to go wrong. And all the methods and classes are checked at runtime. So why? Well, everyone thinks, okay, you may have just reinvented GObject. No, because our base class is more extensive. It does do more than GObject does. It was intended to unify all of our existing ad hoc object stuff, so it has to have the same core features we already have. We don't actually have to write a lot of code ourselves. We now have code generators. So you write a file that defines your class, and your code is actually all generated for you, and just fill in the functions, fill in the squigglies, the curly braces. We have all our method checks are runtime. So in something like GObject, it uses function pointers that are exposed from the object. If you were to cast it to something else, you can call the wrong function if you do wrong casting. With ours, we don't do any casting at all, so we actually check if that method is available at runtime each and every time. We do a really, really elaborate bunch of object indirection, so you can no longer have an invalid pointer. So it works so one of the reasons we now do indirections for pointers is that for many years, EFL has actually looked a lot like GTK in the G world. You have a pointer to an object, and when you try and access an object, we dereference that pointer if it's not null, and we go and look at a special number of bytes in the object. That's an int, about 4 bytes worth of data, and that has to have a magic value in there. And these values are different for every type of object. If it's the wrong type, we return and say, no, you can't do this. You safely return and don't do anything and complain on standard error. There is a slight problem with this mechanism, that if someone passes in an invalid pointer that's pointing to somewhere that is not real memory and you check your magic number, you crash. And the real problem here is that we keep getting bug reports filed that you have a bug in EFL, you have to go fix it, it's crashing during this magic number check there. And you have no idea how many times this happened, a lot. And it was actually quite annoying, trying to explain, saying, no, it's not a problem here, you're passing in a garbage pointer. No, that didn't work. So what you do is you have to actually debug that person's application, find the bug, actually fix the bug for them to demonstrate that it's not your bug. So the real reason we do this now is to avoid this problem. Just because the backtrace ended in EFL, that's enough to say that it's an EFL bug, according to people. So we actually ended up spending something like 60-70% of our time, instead of debugging EFL, we're debugging applications. And of course it takes longer because it's someone's code that you're not familiar with and you have to find their bug. It wastes our time, so that's a lot of time wasted. It also means that applications crash while the user's actually trying to do something useful. And users don't really take very kindly to an application magically disappearing from their screen when they're in the middle of doing something. They would probably prefer to have it gracefully degrade and go weird than have it just magically disappear. And it's also really annoying to have to keep telling people what backtraces are, how memory works, etc., etc. So we needed a solution that's safer. So this is what we came up with. So instead now, for compatibility, every object pointer looks like a pointer, but it's not. What we do is either a 32-bit or 64-bit value on 64-bit in which we stuff an ID. And that ID is stealing an idea from Windows. We have a generation count. And Windows people actually had a really good idea there. And so we have a generation count, you have a table, and then a row entry. So every one of these gets split up. We go find the table it's in, we look at the row. The row also has a generation count with the object. If the generation counts don't match, that means the row has been recycled and a new object has been put there during a different generation of allocation. If the generation count matches and the row has a non-null entry, then we can actually go and access the actual object very, very safely. This means basically no more crashes ever again. Although the downside is it begins to look like a dynamic language. It looks more like your Pythons, JavaScripts, Luas, etc. of this world. So we only use the pointers, as I said, for compatibility. Because our other APIs return pointers, we still keep doing that for ABI purposes. So on 32-bit, we use 9 bits for the generation count. That means you have about a chance of 1 in 512 of, if you've recycled a row, of accidentally getting through the check. On 64-bit, it's an insanely very large number, 29 bits. So that's about 1 in 500 million of getting past that. That's assuming that that row